In science class, somewhere around age 11, most of us pushed a copper coin and a zinc-coated nail into a lemon and watched a tiny LED flicker on. The chemistry is simple. Two different metals in an acidic medium create a voltage difference, and electrons flow from one metal to the other. That flow is electrical current. Now consider this. Your garden soil is already slightly acidic. It holds water and dissolved minerals, and it contains more available ions than most commercial battery electrolytes. Your garden is not a lemon. It is considerably more capable than a lemon. Two pieces of the right metals, buried 6 inches apart in moist garden soil, will produce between 0.8 and 1.1 volts of steady direct current, and keep producing it around the clock without any maintenance for as long as the soil stays damp. Type 1 in the comments if you have already run an earth battery experiment in your garden, and 2 if this is the first time you're hearing that the same phenomenon that powered Victorian telegraph lines might also be feeding your tomatoes. What follows is a story that begins in Scotland in 1841 and ends in your backyard this season. Alexander Bain was a Scottish clockmaker with an unusual habit of solving engineering problems that everyone around him had accepted as fixed. In the early 1840s, the dominant problem in precision timekeeping was the battery. Chemical cells using zinc plates dissolved in acid were the standard power source for experimental electric clocks, but they were expensive, they corroded their containers, they required regular refilling, and they were unpredictable. Bain decided to try eliminating the battery entirely. In 1841, he drove 2 metal plates into the damp ground outside his workshop, 1 copper, 1 zinc, and connected them with a wire. He put a simple galvanometer in the circuit to measure the current. The needle moved. The earth itself was generating voltage. He documented the observation, refined the plate configuration over the following months, and filed British patent number 8783 in 1843, describing a method for using the electrical potential of the ground to drive clocks and telegraphs without any manufactured battery at all. Bain's earth battery was not a footnote experiment. It entered commercial service. Telegraph stations across Britain adopted buried copper and zinc plates as a supplemental power source for sending signals across single-wire lines, with the soil itself completing the return circuit, a method that allowed operators to stretch transmission distances and cut the cost of copper dramatically. Engineers documented the performance factors in detail, align the plates north to south, drive the zinc plate deeper than the copper, and maintain adequate soil moisture for consistent output. Dry summer months reduced the current. The first autumn rains brought it back. The voltage per cell was modest, typically around 1 volt, but it was steady, reliable, and completely free. In an era before power grids, before central generating stations, before rechargeable batteries, a current source that ran on nothing but buried scrap metal and ground moisture was extraordinary. Then, in the early years of the 20th century, the buried plates began attracting attention for a completely different reason. Telegraph linemen and railway maintenance workers began noticing something that had no official explanation. In the stretches of field and embankment where copper and zinc plates lay hidden underground, the vegetation directly above them was visibly different from the surrounding ground. Grass was darker green and noticeably thicker. Crop plants where the plates happened to sit beneath agricultural land showed heavier growth and earlier maturation than the rows around them. No one had added fertilizer. No one had changed the irrigation. The only variable was the buried metal and the quiet current it was generating. These observations didn't make it into scientific journals. They moved the way most inconvenient agricultural knowledge moves, by word of mouth, through station masters and farmhands and groundskeepers who noticed what they noticed and had no framework for explaining it. A Yorkshire station master pointed out the unusually lush strip of grass running alongside a buried telegraph line. A groundskeeper in Essex remarked that the vegetation seemed to know exactly where the buried wire ran. The pattern repeated across dozens of sites, but without controlled conditions, without measurements, without anyone in a position to investigate systematically, it remained anecdote. In the early 20th century, An American physician named George Starr White became one of the first people to seriously attempt to bridge that gap. White was a practicing doctor with a parallel obsession. He believed that natural electrical currents in the soil, what he called telluric electricity, had measurable effects on plant physiology. He ran field experiments, gave lectures, published pamphlets, and collected observations from farmers who reported unusual growth wherever the ground carried a steady electrical gradient. His work was too scattered and too poorly controlled to constitute scientific proof, and he knew it. But the consistency of the reports convinced him that something real was driving the pattern, even if the mechanism wasn't yet understood. Understanding the mechanism required waiting for plant physiology research to catch up. It finally did, and what it found explains everything those Victorian linemen were seeing without being able to explain. The exact build that any gardener can set up in an afternoon, including how to test it with a multimeter and what to log each week, is coming up right after this. Hit subscribe so you get the follow-up video where we run a full season trial and publish the numbers. When copper and zinc are buried in moist, slightly acidic soil, the chemistry is the same as in that childhood lemon experiment, but the medium is richer. Zinc is the more reactive of the two metals. It begins oxidizing immediately, releasing zinc ions into the surrounding soil and pushing electrons through the connecting wire toward the copper plate. The copper acts as the cathode, accepting those electrons. The soil, carrying dissolved minerals and ions, bridges the two plates electrically, functioning as the electrolyte in a battery where the casing is the earth itself. This process is called galvanic action, and it has three effects on the surrounding soil that are directly relevant to plant growth. First, the ionic movement. As current flows through the soil, it mobilizes ions that would otherwise remain locked in stable mineral compounds. Phosphates, calcium ions, and potassium complexes that are chemically inert under static conditions begin migrating under the influence of the electric field. The process resembles electrolysis on a very small scale, the same mechanism used in electroplating and water purification, now operating in your garden bed. Nutrients that were present but inaccessible shift into forms and locations where plant roots can actually reach them. The battery doesn't add fertility, it unlocks what was already there. Second, the pH shift. Near the zinc anode, the oxidation reaction produces a slightly more acidic local environment. Near the copper cathode, conditions become marginally more alkaline. These small gradients affect the solubility of specific nutrients. Iron, manganese, and zinc itself are more available under slightly acidic conditions. Others move into solution near the cathode. The net effect depends on initial soil chemistry, but in most garden soils, the gradient tends to increase the availability of micronutrients that are chronically in short supply. Third, and most directly relevant to the plant growth reports, the electrical field itself triggers a documented biological response in root systems. Plant physiology research dating from the 1970s through to more recent work has confirmed a phenomenon called electrotropism. Roots actively orient their growth in response to electric fields. In controlled laboratory conditions, roots bend measurably toward the cathode, the copper plate, when exposed to voltage gradients as small as 1 millivolt per centimeter. The field strength in a properly set up earth battery falls precisely within this range. What this means in practical terms is striking. The roots of plants growing near buried copper and zinc plates don't passively encounter the mobilized nutrients. They actively grow toward the zone of maximum ionic activity. The electric field is both unlocking nutrients and directing the root system toward the region where they are most concentrated. A 2021 meta-analysis reviewing decades of root electrotropism research confirmed that this response is consistent across plant species, including major food crops, at voltage densities comparable to what a copper-zinc earth battery generates in typical garden soil conditions. The backyard trial that has now been replicated across dozens of independent gardener experiments produces consistent results. In the most carefully documented version, a grower in Connecticut ran 2 identical rows of lettuce side by side for 4 weeks. One row had copper pipe and a galvanized zinc nail buried 6 to 8 inches deep on either side of the root zone, connected by insulated wire above the soil surface. The other row was the control. Every variable, soil type, watering schedule, seed variety, sun exposure, was kept identical. At harvest, the electrified row averaged 38 grams of wet biomass per plant. The control averaged 26 grams. That is a 46% increase in harvestable yield from a system that costs nothing to run after the initial setup and can be moved from bed to bed at the end of each season. A multimeter reading at the copper and zinc connection registered 1.03 volts, squarely within the range Bain documented from Victorian telegraph installations and matching the output reported by gardeners across dozens of independent trials. The voltage held steady throughout the growing period, dipping slightly during dry spells and recovering after irrigation. The statistical analysis of the 4-week growth data produced a p-value of 0.04, just below the conventional threshold for scientific significance. One well-run backyard trial is not a peer-reviewed study, and the honest position is that results vary with soil composition, moisture levels, plant species, and installation precision. But it confirms that something measurable and repeatable is happening, and that it happens consistently enough to be worth running in your own garden with your own data. Here's the setup. You need a length of copper pipe or heavy gauge bare copper wire. 6 to 8 inches is sufficient for most beds. For the second electrode, use a galvanized nail or a strip of zinc metal of similar length. These two metals are the core of the system. You also need a short length of insulated wire to connect them above the soil surface, and a multimeter to verify output. Push the copper into the soil on one side of your plant's root zone, about 6 inches deep. Place the zinc on the opposite side at the same depth. Keep them 8 to 12 inches apart, close enough for a useful electrical field, far enough that they don't interfere with each other's reaction zone. Moist soil is essential. In dry conditions, the current drops significantly. The system depends on dissolved ions to carry charge between the plates. Strip the wire ends and connect one to the copper and one to the zinc, keeping the connection above the soil surface where you can inspect it. Touch the multimeter probes to the copper and zinc, positive probe to copper, negative to zinc. A reading between 0.8 and 1.1 volts confirms the system is active. Log the voltage and soil moisture every few days. Replace the zinc component when it shows visible corrosion, typically after 1 to 2 growing seasons. Run a proper comparison. Set up the copper-zinc pair in one bed or one row. Leave an identical adjacent row without any metal. Keep all other variables, watering, fertilizing, seed variety, identical. Weigh your harvest at the end of the season. Log the difference. Your data matters, and the more people who run careful trials, the better the collective understanding of where this effect is strongest and under what conditions it can be relied upon. The fertilizer industry spends considerable energy on the message that soil fertility comes in bags. Alexander Bain proved in 1841 that the earth itself is a battery. The plant biology research proved that roots know how to use it. The hundreds of independent garden trials run since then suggest the two facts are connected in ways that the mainstream gardening conversation has been notably slow to acknowledge. You have the materials, you have the instructions, you have the multimeter reading, the current is already there. What will you find when you measure yours?